So yesterday we saw that the existence of a thermodynamic limit imposes the fact that our Hamiltonian must have a local structure. So namely, the Hamiltonian is the sum of local operators. So today we start trying to answer the first of our questions: what is a quantum phase? And what is a quantum phase transition? So in order to start with this topic, we must understand that a quantum phase is a property of equilibrium. So, as we said yesterday, the fact that physical systems reach equilibrium is the most fundamental fact of nature. So we need to, be a bit more precise and define what it means to be at equilibrium, away from equilibrium, and away from equilibrium in quantum mechanics. So, do you have an idea? What does it mean to be at equilibrium in quantum mechanics?
Expectation values don't vary with respect to time.
Okay, so this is it's too good of an answer. It's a very good answer. So we will start with the stronger definition that is less good than your answer, actually. But we will get to the very correct answer that is about expectation values not changing in time. But so this answer needs many caveats and caution, because if you take it literally, like all the possible expectation values do not change in time, then it's equivalent to saying that the wave function of the system, psi of t, does not really depend on time, is steady. And what does it mean? So what does it mean that psi of t does not evolve in time? So first of all, remember that we are considering a closed quantum system. Which means that the time evolution is generated by the Hamiltonian by simply exponentiating the Hamiltonian. And because the Hamiltonian is Hermitian, this means that this is a unitary operator. And we will see that unitarity will play a lot of role in the following. And by psi of t, the wave function, we just mean ut psi at the initial time. From now on, when I write psi of t in this way, so without the cat, I will usually mean the density matrix. So psi in general will be, I will mean this, if it's a pure state, or something else if it's not a pure state. Okay? However, sometimes I will be sloping the notation, and if I write something like this, it's obvious from the context that, and this is an operator, that then by psi in this way I mean the cat, right? Because it can only be the cat. All right. So how does the density matrix evolve? It evolves according to the adjoint action, meaning this thing. And similarly, other operators that are not the wave function evolve in what you usually call the Heisenberg picture in this way. Okay. So this not depending on time means that psi of t must commute with u of t. And this is guaranteed if psi of 0 commutes with the Hamiltonian. So this means that any function psi, if commutes with the Hamiltonian, then it will not evolve in time, right? Because then it will commute to the unitary operator, and therefore this will be equal to psi of 0. So this means is our definition of psi steady state, and therefore all the expectation values taken in this state will also be steady, and this is what we mean by equilibrium. And of course, not being away from equilibrium just means that our wave function does not commute to the Hamiltonian. So what kind of wave functions does commute to the Hamiltonian? How can you, is there something, do you have to check every time, or there is a way to construct wave functions that do commute to the Hamiltonian in general?
Eigenstates.
So eigenstate obviously do commute to the Hamiltonian. So there are trivial steady states, right? But in general, this is true, so psi is steady every time that psi is a function of the Hamiltonian. Eigenstates are obviously a function of a Hamiltonian because every Hamiltonian admits a spectral resolution, meaning we can write it in this way. So you see that eigenstates are a function of the Hamiltonian, because the Hamiltonian is just the sum over the eigenstates. But there are other possibilities. The most remarkable of which is the Gibbs state. What Z is the partition function. So it's a normalization. So the Gibbs state is an equilibrium state, and in particular, we will see that characterizes what we call a specific way, kind of equilibrium that is thermal equilibrium. Okay. Okay, so now we know what are equilibrium states. So whatever we want to say a quantum phase is, must be the property of states like this. Okay? So, but now we have a very ample choice of states. So which one do we choose? So first of all, this choice is not set in stone. In fact, there are modern developments in which people are starting to consider high energy eigenstates, which before would, people would not think that the concept of phase may depend on high energy eigenstates, but now, this is a field in development. But usually, we want to consider the most physical type of equilibrium, which is thermal equilibrium, okay? So to define the concept of quantum phase, we could take the Gibbs state. However, we really want to understand what is a quantum phase. So you see that when you have a thermal state, you have thermal fluctuations. Why do you have thermal fluctuations? Even classically, why do you have thermal fluctuations? Yeah? Yeah, because a thermal state is a distribution of probability. So this means that not only you have, for every observable, you have some expectation value, but you also have a variance given by that expectation, by that distribution probability. You will use it to compute the variance, right? Plus, we have quantum fluctuations due to the fact that in every quantum state, there are quantum fluctuations because a state is a coherent superposition of some basis states. So if your observable is not, depending what are the eigenvalues, you have fluctuations that are also of quantum nature. So if we want to understand the purely quantum nature of a phase, we must get rid of the classical fluctuations that are due to the temperature beta. A more modern way of saying this is that this is a mixed state. So in a mixed state, you have both quantum and classical fluctuations, but you want a pure state. And I remind you that a pure state is something that cannot be written like the convex combination of other states. So apart from the trivial that it's the state itself. So a pure state is something that you write like this, whereas a non-pure state is something that you can write like this with I greater than 1 with some probability. So whereas here you have probability 1 of being in the state psi, so that there is a basis in which this density matrix can be written like this. The basis in which this one is diagonal, in fact, this one is, P1, Pn. So here you have a trivial probability distribution, here have a probability distribution. Of course, the sum of all these probabilities is 1, which is also the reason why the trace of a density matrix must be 1. Okay. So asking this means that there are no fluctuations due to this distribution probability. So we want a pure state. Okay. So you see that this is not a pure state. It's a probability distribution where this probability of being in this eigenstate is given by the Boltzmann factor. However, if you send the temperature to 0, beta infinity, this becomes the ground state. And the ground state, so now I say something not perfectly true, so let me say it, is pure. So why this is not perfectly correct?
Could be degenerate?
What?
The ground state could be degenerate?
Yes. So if the ground state is degenerate, then this becomes the projector onto the ground state, which is, there is a probability distribution, and being the projector is with equal weights, so it's again a mixed state. However, it's almost pure, because typically the degeneracy in realistic systems is very low. So this means that either it's pure, or the classical fluctuations are weak. Moreover, we will see that in really, really realistic situations, it's really pure. So mathematically, it's the projector that is not pure, but we will see today at the end of the lecture that because of spontaneous symmetry breaking, you actually choose where to go. So physical ground states typically are pure states. So because of all of this, we want to say a quantum phase is a property of the ground state wave function. Okay. So what property? Which property? So the property, we will construct this notion in many lectures, because as people have refined this notion, they've discovered more things, or they had to refine this notion because they discovered more things. But what we have in mind is this. So imagine that our Hamiltonian is not just a given Hamiltonian, but it's a family of Hamiltonians depending on some parameters. Okay? And it's smooth in this parameter. Means you can take all the derivatives that you want. So for every choice of this parameter lambda, you can find the ground state. So this means that also you have a family of ground states. And now you can put them on a manifold, right? So you have some manifold that has coordinates. So the point lambda has coordinates lambda 1, lambda n. And to each of these manifolds, through the diagonalization of the Hamiltonian, you have another manifold of quantum states. So you see that because of this, I can change slowly my lambda. So I can have a curve, for instance, on my manifold. And then something will have to happen here, right? So the notion of quantum phase that we will build is something like this. Imagine that psi 0 of lambda and psi 0 of lambda prime are equivalent under some respect, under some physical requirement. So there is some equivalent relationship. Equivalence relation. So if they are equivalent, we say they are in the same quantum phase. So many of our discussions will be devoted to understanding what is this. Okay, so this we will refine it in many ways. So let's do the first try. So let's try to borrow notions from classical statistical mechanics, in which you already, even there, you have phase transitions. And do you remember what is a phase in a classical phase? So when you do classical statistical mechanics, what is the most important object? The one from which you derive everything? Free energy, okay? Free energy E minus Ts, and then we will be concerned in particular with the free energy density that we know by now that it is well defined in the thermodynamic limit if we have done things properly. That is this. Okay. So free energy is a function of the state, right? So it depends on the configuration of your classical system. And what is a phase? So if this is the space of your possible configurations, what is a phase? A phase is a domain of analyticity of F. So if you compute the free energy density, you see that this function is almost always analytic, apart from some places that have typically codimension 1. So they're like walls. And you say they mark the phase boundaries. So something dramatic happens to the free energy here. It means that some derivative explodes. And only in the thermodynamic limit. So it is a property of the fact that the system becomes big. And then we say, okay, but everything is continuous and very differentiable here. So they must be qualitatively similar. We call all these configurations a phase. Okay? So this is what we do in classical statistical mechanics. So we will start by borrowing this definition and adapting it to the quantum case. So this is very easy right now, because in the quantum case, all we are asking is that instead the space being the space of classical configurations is the space of equilibrium states, thermal equilibrium states. But we are at t equals 0, right? So what we will require is that the energy density of the ground state is analytic. So now let me illustrate you in practice what can happen such that this guy is not analytic anymore. So what can happen are basically two situations. The first situation is the following. Let me plot the energy of the ground state here and the energy of the first excited state here as a function of your parameter lambda. Okay? And imagine you have this situation, a level crossing. So that if you follow this eigenvalue as a function of lambda, by the way, if an Hermitian operator is continuous, its eigenvalues, all its eigenvalues are always continuous, so you will never have a jump. So if you follow this eigenvalue and then you follow this eigenvalue, this cross, right? But by definition, what you call E0, the ground state energy, is this. So you see that the first derivative is discontinuous, because here is positive and here is negative. So this means that there is some value of lambda that I will call LC, such that the derivative, the first derivative at LC is discontinuous. Yep.
This can happen for a finite system, right?
Yeah.
So
Exactly. So it's not very interesting. So this is exactly the point. We will be concerned with the next situation.
would you still call it a phase transition?
No. I mean, we call it first order phase transition, but it is not a property of the thermodynamic limit. Or not necessarily is a property of the thermodynamic limit. It can easily happen in a two-level system. You know, you just need to interpolate between two Hamiltonians, like, so if your h of lambda is this, and this is maybe just the projectors onto these two states, then you would have it. So it's very boring situation. So we will not be concerned with this. Everything interesting from the many body point of view happens in the second situation, in which you have the so-called avoided level crossing. So what happens is that for the finite system, they do not cross, and they avoid. However, the gap, delta E, goes to 0 at lambda equal lambda c in the thermodynamic limit. So you see that depending on, actually, this means that some derivative of this guy, so the first derivative is continuous, but some higher order derivative in the thermodynamic limit must be discontinuous. So continuous in the thermodynamic limit.
Is there no level crossing?
Sorry, I didn't hear. What?
Is there no level crossing in case of many particle systems? Do we
No,
experience the level?
no, of course, there can be. There could be. But we don't care. So we only care about continuous phase transitions. So this situation, in which it's a property of the thermodynamic limit.
So the level crossing occurs for any value of n. So
yeah, level crossing does not depend on n.
Mm-hmm.
So we are interested in the second case, as we are interested in the continuous phase transition in the classical sense.
We are interested in this case because this is a property of n going to infinity, which means it's a property of the large system. It's not some microscopic property. We will see that, so things like universality, that we will see what it means, of the critical behavior only happen in this case. Universality cannot happen for a few body system. Because it's something that depends on the fact that many different systems can have some equivalent macroscopic properties, but if your system is small, there are no macroscopic properties, all the properties that.
I don't know why the first case does not occur in thermodynamic limit. What kind of physics?
No. What I'm saying is that it can occur at any n. If it occurs in the thermodynamic limit, it also occurs at smaller n.
The case would also occur in the thermodynamic limit, not just restricted to the.
So it's independent of n. Okay, so for now, we will use this definition as a definition of a quantum phase transition. So we will say a critical point of a point of quantum phase transition is a point where a gap closes in the thermodynamic limit. And this will mark phase boundaries in analogy with the classical case. But these are boundaries of the ground state. Okay? So we will start with this definition, then we will improve it. And okay. So what is this statement of universality that I'm making is the following thing. The typical behavior of the gap for lambda close to the critical point is found to be something like this. There is some energy scale J, and then there is lambda minus lambda C to some exponent that I want to call Z times nu. So these are called critical exponents. Now, universality in quantum phase transitions, so there are two types of universalities. There are universality deep in the phase, a universality of the critical point. So now we're talking about the universality of the critical point. Means that the critical exponents do not depend on the details of H. So this means that there are many H's that have the same critical exponents, the same phase boundaries with similar. The location of the critical point is not universal. This number can change, but the critical exponents do not depend on the details. Another phenomenon that is commonly observed together with this is that correlation length also has a non-analytic behavior and diverges in this way. Which means that near the critical point, psi goes like this. Yeah. Psi to the minus z goes like the gap. For instance, in a typical case that we will study when z is equal 1, we see that correlation length and gap are one the inverse of the other. The scale, one the inverse of the other. But what is this? So what is this guy? What is the correlation length? So the correlation length is something that you define starting from the correlation functions. So correlation functions will be one of the most important objects of our study. We will try to understand in what way actually what a quantum phase is depends on the structure of the correlation functions. So let me define the connected correlation function first. Correlation function in this way. For instance, okay, let me define it this way. In the state psi, which typically for us will be the ground state, so we have some operator that has support on I, some other operator that has support on J, and then we subtract the background value. So these are the connected correlation functions, and the non-connected correlation functions are just this piece. They have slightly different mathematical properties, as we shall see. And a correlation length is defined when, so in case when this happens, so it doesn't happen all the time, but it happens very often that these correlation functions decay exponentially. So this means that they go like e to the minus the distance between I and j. So we use the graph distance, okay? And then there must be here some characteristic length. And this is what we call psi. So when a correlation function behaves in this way, we call psi correlation length. Now you see that if the correlation length behaves in this way, so if you substitute this object in here, then you see that near the critical point, the correlation functions go like d to the minus nu. So this means that you are in some phase, so you are in some phase in which the structure of correlation is that everything decays very fast. But then, near the critical point, this happens, and we will see why. And then this implies that correlation functions decay like a power law. So instead of exponential in d, they decay like d to the minus nu, like some power law. Sometimes this is called algebraic because it's a power law behavior. And in condensed matter, every time you hear the word algebraic associated to some system, it means that there are correlation functions that decay in that system that decay algebraically with the power law. Okay. So now we want to apply all these things. This one I don't need. To a specific case to see what it means. So let's write our model of study, that is the quantumizing model. So we have a graph gamma that has edges ij, and we have what we say an external magnetic field that we call transverse, because it's in a direction that is not the same of this other thing. Transverse magnetic field, and then we have the so-called Ising coupling on all the edges of our graph. Okay, so first of all, so this is the quantumizing model. So I believe that in classical StatMech, you have studied the classical Ising model. Okay, so why this is different? Why this is quantum?
Because of the applied magnetic field in transverse direction.
Correct, because we apply the transverse field in the transverse direction, whereas in the classical Ising model, you have couplings. So you have numbers, right? You have numbers that can have the value +1 and -1, and then you have a coupling like this and a coupling like this, right? Okay, but what? So why does it make it quantum? It's because we have operators instead of numbers?
The sigma ix does not commute with the sigma z.
Yeah. Okay. So the reason is that because this will not commute with this. So it's not just because these are operators on a Hilbert space. If I have this system, what I'm doing is that, you see, all the eigenstates of the system are classical spin configurations that are product states. Some spins are up, some spins are down. A state like this is an eigenstate of this Hamiltonian. There are no fluctuations, right? There are no because there are no superpositions. So, and the expectation values of the energy in this state are exactly the value of the energy as a classical function on the same configuration of classical spins. So the fact that I have written it in a matrix form means nothing. It doesn't make it quantum. However, if this is X, so it does not commute, then the eigenstates cannot be product states in the basis of Z, but there must be superpositions. Therefore, there are quantum fluctuations. And this becomes a quantum mechanical model. So there are fluctuations. There is an expectation value, but this expectation value has a variance because we are in a superposition. Okay, so this is why this is a quantum model. And we want to argue that this quantum model has two phases. One for G large and one for G small. So you see, G is our lambda, is our parameter lambda. In general, lambda can be a number belonging to R to the n, can be many numbers, right? It can be 2, 3, 4, 20, whatever you want. Now it's just one, okay? So this is very simple. And we want to say that there are two phases, and that these two phases are separated by a quantum phase transition. So our manifold now is one-dimensional, right? It's just G. And we have some G large and G small. And we think that there is one critical point, so that there is not just a crossover between small and large, but there is one point in which our energy density, the second derivative, becomes discontinuous. And therefore, then we will say all these states have something in common, and all these states have something in common, and there are two different phases. So let's see what it is. And then we also will need to find a way to locate GC, and then to see how the correlation functions and the gap behave, all these things, okay? Okay, so we start our analysis by looking at the very, very easy limit cases. So the first one being G infinity. Okay, so let's see. If there are two phases and they're all similar, it means that instead of studying some specific value of G, I can choose as G small G equals 0 or G equal infinity. So let's start with G equal infinity, first case. So if G goes to infinity, it means that I can just neglect this piece. Okay? And we are interested in the ground state. So the ground state for G infinity, what it is? Who will tell me what is the ground state?
The line in the x direction.
Speak up.
X direction
in x direction, which we will call plus. So it's the tensor product. So by plus, I mean the state 0 plus 1 over square root of 2. And what I mean by this, I mean that sigma z 0 is equal to 0. So I am in the so-called z basis. Or in other words, this is what we call spin up and spin down. So you see the ground state is unique, first of all. And it's also very simple. It's a product state. If you compute, there are two objects that we want to compute, and one is the magnetization. Then we will see why. That is defined as the 1 over the total number of spins, the expectation value of this guy, the sum of over all the sigma z's. And this is equal to 0. So this is the average magnetization in the z direction. Because it's 0, we say there is no magnetization. Actually, we say there is no spontaneous magnetization. So now the question is, well, we got 0 because we looked at it in the z direction, right? If we looked at the magnetization in the x direction, we would get 1. So there is magnetization. So it seems arbitrary. So why do we do that? Why this makes sense and not computing it in the x direction? Why we conclude saying that, so in every book, you will find that for G large, so in particular, this is a paramagnet, PM. And by paramagnet, we mean this. However, in the x direction, it's not 0. So why it's a paramagnet? What is special about Z?
Can you repeat the question? Like, why?
So, you see, it seems that the value of M depends, so whether it's a paramagnet or not, it depends whether I compute it in the Z or X direction. So the question is, why in the Z direction? Why X direction is no good?
It's transverse to the lattice.
Sorry?
Z is perpendicular to the lattice. Is that why?
Z is perpendicular to?
The lattice, the 2D lattice.
No.
That's not why.
No.
In case of icing Hamiltonian, Z direction give is an interacting term between the spin. So I think that is the
No. So the point is that we want spontaneous magnetization. So you remember how you find spontaneous magnetization in a classical system? You compute the magnetization for the finite system, then you take the thermodynamic limit, and then you send the external field to 0, and you see that there is a residual magnetization, even if there is nothing from outside to orient you in that direction. So there is a magnetization that is not imposed from outside. But when this is our Hamiltonian, right? So magnetizing in the x direction is not spontaneous. It's because we have a term that magnetizes us in the x direction. So we want magnetization in a direction that is not x. So we could compute it in the z direction, even if we had an external field in z, then send z to 0, and see if there is something left over. And the answer is no, there is nothing left over. If you have an external field in the z direction, and then you send that field to 0, the ground state is this one, and you compute the spontaneous magnetization, it is 0. So that's why we choose z. if you compute the correlation functions, and now let me compute the non-connected correlation functions, not connected. Actually, for this case, this result does not change, but they're also identically 0. However, which of these properties are a property of the phase? Okay? So the property, not just of this specific point, G infinity, but of all this range of points. Okay, so this one, yes. But for G not infinity, but G large, we get a result that is compatible with this, but it's different, and we get exponential decay. So a way to compute this is to do perturbation theory around this ground state, and then expanding it for G large, which means 1 over G small. So means that you add this term as a perturbation, starting with this ground state, and you compute the corrections to the ground state, and you compute the new correlation functions, and you will see this behavior. So you will do this in the tutorial. Yeah?
Why are you calculating the not connected correlation function? Why don't you use the previous expression in which you substitute?
Yeah, okay. So for this case, there is no difference.
Yeah.
There is no difference.
In general, what should we do?
But when we see the other limit, there is a very subtle difference that, so here I could have used the connected ones as well. It's the same thing. But in the next case that is much more interesting, we will see that there are many, many subtleties. And there is a difference between connected and non-connected correlation functions. I'm going there in 1 minute.
The result for the G large is the connected one or a disconnected one, or is it?
It's the same. It's the same. So in this phase, there is no subtlety concerning connected or not connected correlation functions. Okay. In the G small phase, the situation is much richer, and we see it right now. Okay. So the other case, the other limit is G going to 0. So this means that our Hamiltonian is this one. Now, something that we have to notice that not only in the limits, but, so let me write it here. For every value of G, our Hamiltonian, that is this, right? I could have written it here. This is a family of Hamiltonians parameterized by G. Our Hamiltonian has a global symmetry, a global Z2 symmetry. What does it mean? It means that there is a Z2 group whose representation are operators that commute with the Hamiltonian. So means there are two operators that commute with the Hamiltonian. One must be the identity, and the other one, let me call it T, is what we call the global, if you want, spin flip. It's a non-local operator. It's a global operator that flips all the spins. And you can see that for every value of G, they commute. By definition, this is a symmetry of the Hamiltonian, operator that commutes with the Hamiltonian. Okay? Notice that, okay, so this is a cat, but these two statements that are equivalent, under this operation, this state goes into itself. If you write it as a density matrix, you can write it exactly in this form, that H and psi 0 also commute. So in other words, the Hamiltonian and the ground state have the same Z2 symmetry. All right? Now let's see what happens here. Okay. When G is equal to 0, what is the ground state of this Hamiltonian? Now,
It's an ordered phase.
huh?
It's an ordered phase, either upward.
Yes and no. I mean, you are almost right. Huh?
Depending on the sign of G.
No. Regardless of the sign of J, it's true that all spins up and all spins down are ground states, regardless of the sign of J. Anyway, J is greater than 0. So your colleague is right when he says that the global spin up, let me call it just 0, and the global spin down are ground states. But the complete story is that the ground state is a subspace. It's not two states. So it's a subspace that we call L, and it's all the possible linear combinations with complex coefficients of these two guys. Okay, so now I'm not being just picky mathematically. This is important. Because as you can see, these two states do not enjoy the same Z2 symmetry. So, in other words, T and 0 do not commute, and the same for 1. In fact, their algebra is the following. Right? T is exactly the operator that flips all the spins. So, if they roll up, they go all down, and vice versa. So we call this symmetry breaking. So by symmetry breaking, we mean that there is a symmetry of the parent Hamiltonian that is broken by the ground state. So this ground state does not have the same symmetry of the Hamiltonian. However, not every state in this subspace is a symmetry breaking. In fact, if you build these two states, psi plus minus, that are these two, the symmetric and antisymmetric combination, you easily see that they commute with T. Their density matrix commutes with T. So these have Z2 symmetry. What about all the others? Right? What about all the other combinations? So you can easily prove by yourself that every other combination is symmetry breaking, but this one is the one that is maximally symmetry breaking. What does it mean maximally symmetry breaking? It means that if you take your state that is some linear combination in this space, you compute the commutator, and then you try to see how big is this commutator. The biggest one, so the max overall, so to say big, we take the norm. A commutator is an operator. In a Hilbert space, operators have a norm. The norm right now that we are interested in is the operator norm. Do you know what it is, the operator norm? So tomorrow we will talk at length about norms, but it is this thing. So first of all, in a Hilbert space, you have a norm for vectors, right? So if this is a state vector in a Hilbert space, the norm of V is the square root of the scalar product of VV, okay? then if A is an operator, let's say a bounded operator on H, then the operator norm is the sup over all the V that have a norm 1. Now this is defined of AB. You see, because AB now is a vector, so the norm of this is given by this formula. So what we do is that we evaluate the norm of an operator by evaluating the maximum norm of the vectors that it can reach. Okay, so this is operator norm. So when we say that these are maximally symmetry breaking, it means that this maximum is reached for 0 and 1. Okay? So all the others have a smaller commutator than this one, and this one have commutator 0. So also the norm is 0. So you see that whether we have symmetry breaking or not, it depends on which states we select in here and how much symmetry breaking there is. Now, the reason why in books you often find this statement that, oh, this is the ground state, this too, is true, but it's a very profound and subtle physical statement. And it means that for some reason you believe that only the maximally symmetry breaking states are the physically relevant. So we will talk at length about this. This is called spontaneous symmetry breaking. It means that you will only find states like this and like this. You will not see the ones that do not maximally break the symmetry, that your system spontaneously chooses that. And yeah, time is up. So tomorrow I will explain to you why this is so, why there is spontaneous symmetry breaking. So to come to your question, let me notice that the structure of correlation functions also depends on this. In fact, connected correlation functions are 0 also in these states, but they are different from 0 in these states. So now it depends on whether you choose the symmetry breaking or non-symmetry breaking combination. The non-connected correlation functions, okay, so if you compute both the magnetization and the connected correlation functions, you find 1. However, the connected correlation function becomes 0 again. And in order to find a non-zero value of the connected correlation functions, you must use these states. So this has a profound implication that we will explore at length. If you do perturbation theory, you will see that the magnetization that is 1 for G equals 0, as you increase G goes down. And if you can continue the perturbation theory until the critical point, that we don't know right now where it is, it does something like this. So that's why we call this phase a paramagnet, because there is no spontaneous magnetization, where here there is a spontaneous magnetization in the z direction. You see, this is interesting because the Hamiltonian is symmetric under T. However, for small g, there is a finite non-zero value of the magnetization in the z direction, spontaneous. Okay, that's all for today.